Pain-related conditions are commonly cited as a reason to use medical cannabis, and the reason for that is because they work. Research shows that cannabis is effective as an analgesic, and not only that, but several proposed mechanisms are out there as to why. In this video, I'll be explaining one of these. In short, CB2 receptor activation through selective agonism is effective in the peripheral release of endogenous opioids. And what this means is that endocannabinoids stimulate the release of naturally produced opioid compounds in our bodies. Activation of CB2 can result in an inhibition of thermal hypersensitivity and tactile hypersensitivity in neuropathic pain models. CB2 activation does not result in any central nervous system effects, so that is important since one major downside of many analgesics is that they do, in fact, cause CNS effects, such as opioids, which can limit their usefulness. The cellular target here is keratinocytes, which have been reported to have endogenous opioid peptides and CB2 receptors. The hypothesis tested here is that when keratinocyte-derived CB2 receptors are activated, they will release the endogenous opioid beta-endorphin and relieve pain. The experiment was done on male Sprague dolly rats and also mice, and the drugs that were used were CB2-specific selective cannabinoid agonists, which is to say that they target a specific CB2 receptor. The researchers implemented the hind paw withdrawal latency test to test for pain response, as I described in my previous video about CBD and arthritic pain, link in the description. A heat lamp heated a platform that the hind paw was situated on, and the time that it took for the rat or the mouse to take their hind paw off was measured under the different testing conditions. A smaller withdrawal latency would mean that there is more thermal hypersensitivity and therefore indicates more pain response, which is one thing that CB2 activation is supposed to minimize, according to this hypothesis. In a nutshell, the drug reduced thermal hypersensitivity. Paw withdrawal latency was increased by 55%, meaning that it was able to keep the paw on the heated platform for an extra 55% longer. Use of naloxone actually eliminated the pain-killing effects of the drug, naloxone being the opioid antagonist. And this means that endogenous opioid secretion plays a part in this. But is it beta-endorphin? To confirm their hypothesis, an anti-serum for beta-endorphin to neutralize the effect of beta-endorphin actually also prevented the anti-pain effects of the drug. This graph shows BL as baseline, and the rest of the bars represent the drug conditions. First, the drug with no neutralizing serum, then naloxone, the beta-endorphin anti-serum, and the one on the far right, a control serum to prove that the serums that are meant to neutralize activity are doing it by virtue of their biological activity as a kind of control. Now, they also wanted to see if taking away the mu opioid receptor that this endorphin works on would do anything. If the rat or mouse has the receptor and still the drug causes anti-pain effects, this could confirm that this is at the level of the mu opioid receptor, and therefore that endogenous opioid secretion through that receptor is the culprit. What they found was that in the rats with the receptor, the anti-pain effects are present, with a 127% increase in paw withdrawal latency. The animals without their receptor saw significantly less effect when administered the drug. The white bars show receptor-deficient rats. Notice how the paw withdrawal latency is way lower in that group across the board, while in the rats with the receptor, you actually see a dose-dependent relationship as the dose increases, which suggests that the drug is causing this decrease in response to painful stimuli as you add more. They also tested the CB2 receptor by using CB2 antagonists with the drug to see if it's actually working through activation of CB2. And they did find that CB2 receptor antagonists reduced endorphin release back down to the level of control. Some of the rats were also bred to have no CB2 receptor, and they found that endorphin release was also diminished compared to those who were given the drug with the CB2 receptor. Using receptor-deficient animals, using antagonists, and drug-neutralizing agents are three ways in which this study pins down the reason why there was pain relief and the receptors that it works through and the compounds that it used. The receptor-deficient animals will not show the improved response without the receptor targeted here if it's working through that receptor. The antagonists antagonize the action of the receptor when it does exist to see if the effect would be dampened if given with the drug. The drug neutralizing agents neutralize the drug itself and see that if used together, the response is dampened. And this is all to come to the conclusion that the pain relief shown in the experiments occur by using a CB2 dependent mechanism, to increase production of beta endorphin on the level of the mu opiate receptor, ultimately relieving pain. Now, CB2 does a lot of things in a lot of different places, so we should understand that this would have more wide-reaching consequences if administered systemically in other areas. But one of these effects seems to be the pain relief through a CB2-dependent mechanism. And this result in rodent keratinocytes has been also demonstrated in cultured human keratinocytes. Anyways, that's about all I have for you guys today. If you want to help this channel, leave a like down below. Tell me what you think about this study or what concept you'd like to see me explore next. Don't forget to subscribe to the channel, and until next time, stay meducated.